Okay, it's about time to start. Okay, I received a few emails from students concerning homework, and in particular the online homework. The main issue usually when I'm getting emails is a question of whether it's accepting it or not, accepting your answer. And I just encourage you to play around a little bit and try different formats, try a fraction, try a decimal, etc. Try standard form for vectors or component form if something doesn't work. Oftentimes it's just picky about how it's taking the answer, and you should be able to sort of answer as many times as you want and get full credit if you get it correct. Also, so I have office hours on Monday. If people need to talk or would like to talk and are having, outside of just their recitation, the recitation is the best place to get homework advice, but please send me an email and I can arrange another time. If I get too many emails, maybe we'll set up a problem session or something, a regular, but hopefully the recitations will help with that. Okay, so today what we want to do is we want to talk about lines and planes and their equations, primarily in three-dimensional space, although for lines we'll be able to really do this in arbitrary dimensions. But before I get to that, I want to say some general words about equations in space, I guess. So let me talk about equations in Rn. So this is n-dimensional space. It's a notation for n-dimensional space. And primarily, for us, n is going to be 2 or 3, maybe 4. Okay. So I want to say that I don't know if people realize this, because often much of the graphs you work with are in 2 dimensions, graphs of functions, but there are really 2 different flavors of equations, especially in multivariable calculus that you encounter. And they're really different. They have different kinds of behaviors and nuances. So one type of equation is what's known as a parametric equation. And the idea is you have parametric refers to the parameters. You have some parameters which will give you sort of an assignment of points on whatever subspace of Euclidean space we're describing. Okay. And then there's another type called an implicit, which I will call an implicit equation. And these guys, well, they say only consider points that satisfy this equation. So it doesn't really make an assignment. It just says, okay, well, we're going to carve out a subspace of Euclidean space with these equations. So let me give, that's sort of abstract, so let me give a concrete realization of this that you've all seen and you all know and love, or at least know. So here's a circle. Okay. And let me draw the circle twice here. So I've got a circle in the Cartesian plane. All right. Now, what is the equation for a circle? Well, you can go and, let's say it's a unit circle. So let's say unit circle. So you can go into different lower level classes and ask that question and you'll get different answers, right? If you go into like a trig class, for example, maybe, I don't know, one of the answers you'll get the parametrization of the unit circle, which is most commonly written cosine t sine t, right? And here you have this parameter t, and you're going to let it vary, say, from 0 to 2 pi. So that's one equation you could get for the unit circle. Now for the same circle, you have another equation, right? X squared plus y squared equals 1. Okay. So these both describe the circle, but how are they describing it? Well, in the first case, you say, okay, well, you give me a single parameter, t, between 0 and 2 pi, and I'll specify a single point on this circle, right? So this is giving me a way of actually saying, okay, think of t as time. At time 0, I start here, and then I go kind of constant speed around the circle. So a parametric equation is giving you some kind of way of sort of describing, well, I guess a parameter on the circle. Now, of course, you can see that there should be then a lot of different parametrizations of the circle, and there are, right? Parametric equations are not unique, not at all, right? I could have started over here on the circle and gone clockwise and then slowed down, had a coffee, and then, you know, kept going, and then kept going, and then really speeded up at the end. So there's a lot of different parametric equations describing sort of, you know, your space and the path that you would take on it. This is for one dimension here. Now for the implicit equation, there's really up to, say, multiplying both sides by some constant or some other function, say, there's kind of one good equation here. And it's just saying, okay, just consider these points x, y that satisfy this guy, this equation. And so in a sense, implicit equations are a little more unique, right? They're sort of more determined than parametric equations. Now, however, as I said, today we're going to look at lines and planes, and it turns out that for lines in three-dimensional space, or indeed for higher dimensional space, the best thing to use, or maybe the easiest equation to write, is a parametric equation. Whereas for planes in three-dimensional space, the best thing and the easiest thing to write is an implicit equation. So they're really different kinds of equations, not just different equations, of course, but different types of equations that we're going to be looking at today. If you go into higher dimensions, lines still are going to be written as parametric equations. Planes will get more complicated. They could be written as sort of using several implicit equations or a parametric equation. But the parametric equation in higher dimensions is a little more complicated. So we'll stick with three-dimensional subspaces. So for today, n is going to be 3. All right, so now what I want to do is I want to describe, we're going to take lines first. I want to describe a line in three-dimensional space. So for that, let's draw our three-dimensional coordinate system. So we have some x, y, z coordinate system. I'll label on my axes. And I'm going to give myself some line, just, you know, say sitting out in space. This is my line. Okay. So now I want to give myself a parametric equation, which means what I want to describe is my parameter again, I'll say is t. So think of it as time t. And at time 0, I'm going to start somewhere on the line. And then I'm going to go in a certain direction, you know, to the right here or the left, let's say to the right in this case. And I'm going to go, say, at sort of constant speed in a certain direction. So my parameter is just going to say, okay, at time t, I'm at this point on the line. Of course, I can also go, I can reverse time and assume that I'm sort of coming from a different direction, you know, the opposite direction, and say, okay, in negative directions here. So here we go 0. That's what I'd like to do. So let me give myself a starting point. I'll say starting point P. This is some point, which I'll call, say, x naught, y naught, z naught. Okay. Why not, right? All right, sorry. So now I'm just going to give myself, so if I'm going at constant speed, then at time 1, well, let's just say at time 1, I hit the point Q on my line. So this is going to be time 1. And I'll give myself coordinates x1, y1, and z1. So as we'll get into, certainly when we do parametric equation, more general parametric equations in chapter 3, and hopefully many of you know this from maybe some physics or something like that. If I want to describe velocity, velocity is best described as a vector in 3-dimensional space. Speed is a number, it tells you how fast you're going, but velocity gives you a direction that you're going as well. And if I started at point P and ended at point Q at time 1, then my velocity vector is just the displacement vector PQ. So I'm going to say the velocity vector here is PQ, and I'm going to write this as V. I'll just label it as V. Now for lines, this vector has a name. We call it the direction, or a direction vector. Put this over here. So V is called a direction vector. Now, I waxed poetic a second ago about parametric equations and said, you know, they're not unique. Of course, this direction vector I just got depends on the displacement PQ. So I could have gone faster, I could have gone in the opposite direction. So there's no single direction vector, but there are direction vectors for a line, and this is one of them. And if we wanted to write this out in component form, that's quite easy. Again, we just have this, we just take the difference of the endpoint Q with the initial point P. So I just have to take it coordinate by coordinate. Okay, so I get a direction vector. Let's draw it, oops. And it's sort of, okay, this is my V. Sort of pointing in the right direction, hopefully. A little bit off. Okay. Now, I want to describe sort of the whole line. So what I want to say is, after a certain amount of time, how far will I go? Well, that's going to be velocity times time. So I'll have gone t times v after a certain amount of time. But what I need to know, of course, is, and I have written in front of me, is also where I start. So I also have this starting point, which is, I'm going to write as another vector, which has terminal point P. So this I'm going to call vector R naught. So R naught is the initial vector. It's a vector in standard, I mean, it's a vector with initial point at the origin, but its endpoint is where I'm starting on the line. Okay, and of course, this is going to equal x naught, y naught, z naught. Okay, so I've got a couple of vectors now. I've got my starting point and I've got my velocity vector. And really, if I want to know where I am at time t on my line, I just have to multiply my velocity vector by the amount of time and add it to R naught. That will tell me how far I've gone and where I am on the line. So, and this is exactly what you get for the parametric equation. This is called a vector parametric equation for the line. Let's call this line L. So we'll call it R of t. And so we start with at our starting point, R naught, that describes the endpoint, and then we add how far we've gone, t times v. This is our equation. Now you can, of course, write this out as, you know, x equals, okay, so if we want, we can write this out. I'll do it really quickly here. as three functions, three parametric functions. Each of them giving us the coordinate of where we are at time t on that particular, yeah. So you can do this if you want, and this is just writing out each coordinate of this vector equation, vector parametrization. Oops. Okay. So sometimes, I mean, the book has this, we'll call this set of three equations a parametric equation. I prefer just sort of the more compact form of a vector equation. All right, so this is how we get the equation. Of course, I mean, what happens when we add this? So let's say we multiply t by our vector v by some constant, some t, I'm sorry. So this is t times v. Then what are we doing when we consider this sum over here? We're just saying, okay, well, take this vector and add it, you know, to R naught. And what you're going to get is, of course, you're going to get the vector that ends here. Okay, just by taking the vector arithmetic. So that's the idea. All right, so let's do a numerical problem just so we're not shocked when we actually have to do a problem. Okay. So let's say find the equation for the line through the following 2 points, say the point P equaling 1, -1, 2, 2, and Q equaling whatever, say 3, 1, -1. All right, so the solution, basically all you need to do, you need to find an initial point, initial vector, and a direction vector. And this is just given, these are both given by the formulas that I've written above. So an initial vector. And again, there's some choice involved here. You could choose Q, you could choose P, you could choose, if you found another point, you could choose that. But we'll just make it simple here and just choose P. And I'm going to write it as a vector. So this is a vector from 0, the origin, to P. And then I need to find a direction vector, which will be PQ. And so for that, sorry, I just take the difference. So I'm going to take 3 minus 1 is 2, 1 minus -1 is also 2, and -1 minus 2 is -3. And then I just simply write down the equation. So now, and again, I'll keep it in vector form, but you can, you can write this R of t as x of t, y of t, and z of t, just the components of R of t, if you want. And this will give you, just by adding up this R naught plus TV, will give you 1 plus 2t, -1 plus 2t, and 2 minus 3t. And that's it. Not hard, right? Questions? Okay. So let's do another type of problem that you'll encounter with lines. Little more difficult. So let's say we have a line and we're given the equation here. So let's say I have the equation x equaling 1 minus t, y equaling 2t, and z equaling 1 plus t. Okay. And I'm given a point R, say equal to -1, 0, 1. Okay. So let's well, I'll just ask, find the distance between this line and this point. So I've given you an equation for a line and I give you some point in space. And I'm just asking you to find the distance between them. Now, whenever you have some geometric object and a point, say, or really two geometric objects, and you're asked to find the distance between them, well, there are a lot of distances, right? Because there are a lot of different points. The distance generally refers to the minimal distance, so the smallest distance. So you want to find the smallest, the point on the line that realizes the shortest distance to this point in space. And that's the answer here that you're looking for. So we have some line, don't we? Yes. Let's get a line here. Okay, so we got a line and we've got a point. Here's our point R, here's our line. So what we're looking for, of course, is going to be that point for which when I draw a line from R to that point on the line, I have a right angle. That's what I'm looking for. And I want the length of that dotted line there. So how do I find that? Well, the point is you can reverse this process of, so a second ago we did a problem of finding an equation for a line. But if you're given an equation for a line, you can pull out an initial point, you can pull out a direction vector from those equations. So you can reverse that process. So how do we do that? Well, if you look up here at the problem we just did, and you look for R0, R0 is just given by the constants, namely those numbers in our equation that don't have a t, that aren't coefficients of t. So if I want to extract R0, I can easily do that by just finding the constants. So a point, initial point, for example, on the line, this is just for general information, is on this line that I'm given here in this problem is 1, 0, 1, right? That's one point on the line. But more importantly than that, we can extract the direction vector, or a direction vector, which is what we're going to want. So a direction vector for this line is going to be given by the coefficients of t. And again, these are not unique, but nonetheless, it's good. Well, we'll call it V, and it's going to equal, in this case, but you can see the coefficients. We've got a -1 here, a 2 here, and a 1 here. I mean, you don't see it, but okay. So we've got -1, 2, 1. So how does this help us answer this problem? How do we get something from this? Well, let's draw a picture here. So this point I'll call P. So I've got this point P on my line. It's probably not going to be the point that's closest to R on the line. It's unlikely, right? And we have this vector V, okay? Oops. So, and again, this vector, let's give it a color or something, I don't know. This vector is not going to, it's also just going to be some vector here. So now what we can do is we can easily look at another vector, right? We can look at the vector from P to R, right? I think. And if we do that, then all of a sudden we get a right triangle. And what we can do is we can look for the angle theta, and we'll see then quite easily that this distance is going to be precisely the norm of PQ, PR, my bad. Let me make it a little bigger. The magnitude of PR times sine of theta, where theta is the angle between PR and V. Maybe absolute values. I'll just keep it there. Okay. Now, okay, but then how do we find this? Well, actually, last time we had an equation for something that had a sine of the angle in it. Do you guys remember? We had the dot product, which is my favorite, which has a cosine theta. But last lecture, we talked about things that gave us a sine theta, and that was the norm of the cross product of two vectors. So in this case, if we're interested in this quantity, which we are, we can write this, we can easily give it a formula for it. We just have to remember a little bit about what we talked about last time. Namely, so theta is the angle between V and PR. And so I'm going to multiply this equation, or this quantity by V, the magnitude of V. But then, of course, I have to divide by it to get an equality. The reason I did that is because now I really can apply this thing we had last time, this equation we had last time. So this is going to equal the magnitude of V cross PR. And do we have everything we need? Well, we haven't written down PR, but we can easily do that. We do have R here and P here. So this is the formula, the thing I'm giving, and you'll find this in the book. This is the distance. Once you find your P and your V, this is going to be giving your distance. And so to compute it, we just need to calculate PR and then do a little bit of arithmetic. So PR is going to be, I take the components of R and subtract those of P. So this is going to be minus 1 minus 1, which is minus 2. 0 minus 0 is 0. And 1 minus 1 is happily 0. That's a great vector, a lovely vector. Okay. Good. So now let's just go ahead and, so now we just need to compute. So if we have everything we need, right? We have PR, we have V, and this is what we need to compute. So we go ahead. So let's take V cross PR. This is going to be given by the determinant of this 3 by 3 matrix, where remember we put I, J, K in the top row. We put V in the second row, which is -1, 2, 1. And we put PR -2, 0, 0 in the bottom row. And we'll see that we get a 0. So I'm just going to compute the determinants. First, I compute this determinant of that matrix, that's 0. Then I need to cross out these two guys, and I'll take another determinant. It looks like I get 2, but there's a negative sign on this, so I'll get -2. And then finally, I'll take the determinant of this 2 by 2 matrix, which looks like it's going to be 4. Okay. And so this is my V cross PR, and of course, all I need to do then is take the magnitude of this vector, and I need to take and divide it by the magnitude of V. So magnitude of V cross PR. This is going to be the square root of the sum of the squares. So this is the square root of 0 plus 4 plus 16, which is square root of 20. And the magnitude of V this is going to be, v is up here, the square root of 1 plus 4 plus 1, which is the square root of 6. So my distance then is the quotient here. So the square root of 20 over 6. I guess 10/3, I don't know, whatever. You can simplify. Okay? Does that make sense? Is it too much? People in pain yet? Hopefully not. No pain. No pain, no gain, right? That's what they say. People have said that. I've heard that before. Okay. So enough of lines, enough of lines, enough of lines. Let's talk about planes for a moment. Okay, so let's say we have a plane in 3 space. Okay, this is going to be some plane. Our planes are going to be described by an implicit equation. And there are 2 things we need. So we need 2 things to make this equation. 2 quantities. Quantities or structures or whatever. Okay, we need a point on our plane. We're going to need a point. And I'll call that point, I guess, P. So here's my point P. And this will be, say, x naught, y naught. So it's P equaling x naught, y naught, z naught. And I need something else. I need a normal vector. What is a normal vector? Well, my normal vector, I'm going to denote it by n. And what it is it's a vector which is perpendicular or orthogonal to the plane. So it makes a right angle to any vector that's parallel to the plane. Any displacement vector of 2 points on the plane is orthogonal to this guy. This is my norm vector. Now, of course, you'll observe, just like direction vectors, normal vectors are not unique, right? I can scale them up, I can go the opposite direction. But up to a non-zero scale, they are unique. So they're kind of unique up to scale. So we want a normal vector. So now we'll get this equation by just asking ourselves about the definition of a normal vector that I just gave. So we will derive the equation very, very simply. If we take a point Q, any point Q on the plane, the way we can ask whether that point is on the plane or not is we can ask about the displacement vector. Well, hopes. Nope. Okay, I'm going to be lazy here. I can ask about the displacement vector from P to Q. Okay. So I'll look at P, I'll take any point on the plane and I'll ask about PQ, the displacement vector PQ. If PQ is orthogonal to N, then Q is on the plane, right? If it's not, then it's not on the plane. That's how we can determine whether Q is on the plane or not. So Q is on the plane. I'm just going to write down what I just said. If and only if, when I take this dot product, PQ, I get 0. That's an equation. So the validity of that equation is telling me whether or not Q is on the plane. And so now all we need to do is turn that into an equation. So we'll turn that into an equation in X, Y, and Z. That'll look more familiar. So my arbitrary point Q, I'm going to give coordinates X, Y, and Z. It's just an arbitrary point in 3 space. And then all I have to do, and my normal vector n, I'm going to give components A, B, C. And then I can write the displacement vector. So this is actually the equation for the plane. Whoa, that's amazing. Okay, so I can write my displacement vector PQ, which is, again, this is just going to be x minus x naught, y minus y naught, z minus z naught. And then when I look at this dot product, well, I could think of it as the dot product that's up on the upper right-hand corner here, upper right-hand screen here, this one here. Maybe you just need to commute the dot product, so n dot PQ. Or I can write it out and see that I'll get something of the form below it. So here I'll just see if I take, pardon me, if I take, sorry, 0 equals PQ dot n, this is going to equal this vector, x minus x naught, y minus y naught, z minus z naught, dot ABC. I expand this out, and I'll get AX plus BY plus CZ plus, or well, maybe minus, some AX naught plus BY naught plus CZ naught. Now notice, as I said, what do you need? You need two things, two quantities, or two, maybe I shouldn't say quantities, but I need a point P. P is given here, and I need a normal vector n. N is given here. They're fixed numbers, is what I'm saying. They're not variables, they're numbers, okay? We find them or we get them in the beginning of this equation. So in particular, when I look at this expression, this is a number, right? It's just a sum of numbers. So I'll call this number D. And if I call that number D, then I get the equation on the upper right-hand screen here of AX plus BY plus CZ equals D. So this is a more common equation, maybe standard form or something of the equation for a plane in 3 space. One notices on the left-hand side, this is a linear equation, right? In the sense that there are no powers of x or anything like that. It's just some linear expression. Okay, good. So the equation for a plane is very easy, okay? Very easy. The challenge in working with problems about this isn't really writing this equation down. The challenge is finding these two things, P and N. So let's do a problem where we need to find these guys. So find, I'll say the equation for a plane, or for the plane, I should say, containing the following points. P equaling, I'll say 1, 1, 1. Q equaling 1, 0, 1. And R equaling, let's say 2, 1, 0. That is okay, good. I believe that's okay. Okay. I'm sort of changing, I don't like my notes very much, so I'm changing them. We'll see if it works out. There is a chance, if you're given 3 points, of course, that they lie on a line. If that's the case, then there's not a single plane that contains them, but many planes. All right. So you'll notice, I said above, that we need 2 things to get this equation. We need a point. Well, I just gave you 3, so we're great there. But you also need a normal vector, this n. So of course, this question is all about saying, well, okay, find that normal vector, find a normal vector, and then go ahead and apply this equation. So the challenge here is to find a normal vector. And how do we do that? Well, we remember that a normal vector is a vector that is going to be perpendicular to the plane or orthogonal to all vectors that are displacement vectors on that plane. Well, I can find a couple of displacement vectors on my plane. So I've got 3 points, P, Q, and R, say. I've got 3 points, so I can find a couple of displacement vectors, right? Here's one. And let's just take the other one here. I'll take PQ and PR. There are 2 displacement vectors on the plane. And I need a vector that's orthogonal to both of them. Does that sound familiar? Couple of vectors and you want a vector that's orthogonal to both? What should you do? I can't hear you. Cross product, great. It's great. Thanks. Cross product, right? That was a great thing about the cross product, sort of the miracle of cross products, right? There should be some cross product. Well, okay, I guess honestly, this is going to go this way. I go PQ cross PR. This will give me a normal vector to the plane, assuming these points aren't all collinear, namely they don't all lie on the same line. So let's check. So of course, to get this quantity or this vector, I need to have PQ. And you didn't have to choose these 2 vectors. You could have done QR and QP or something. I mean, you could have done that. That's fine. But I'm just doing this. So let's say PQ. It's going to be 1 minus 1 is 0. 0 minus 1 negative 1. 1 minus 1 is 0 again. And PR. This guy is going to be 2 minus 1 is 1. 1 minus 0 is 1. And 0 minus 1 is negative. Of course, I did it wrong. Sorry, I was taking QR. Sorry, let me redo that. Pardon me. So 2 minus 1 is 1. 1 minus 1 is 0, and 0 minus 1 is negative 1. But if I make mistakes like that, please do just clear your throat or something. Give me a dirty look. I don't know. Whatever you want to do. I make them frequently, so I try not to, but mistakes happen. So now let's calculate a PQ cross PR. Again, this is going to be a determinant of the following matrix, I, J, K. I'll put PQ in the middle row, and I'll put PR in the last row, third row. And then I just compute. So I get a 1 here for my x variable. For J, it looks like I'm going to get a 0. And for K, I get 1 as well. Or sorry, 1, pardon me. So it's negative of a negative. Okay. So this is going to be a normal vector. And again, once I have a normal vector, this is my ABC. A is 1, B is 0, C is 1. Once I have that, I can easily write down the equation just by using, well, either one here. I'll just use this equation here, but maybe written in the form up on the right on the screen, on the important concept screen. So the equation is going to be PQ. So my Q when I formulated the equation was an arbitrary it's not this Q. This Q is static. So I don't want to use the same Q, so I won't write PQ. I'll just write X minus 1, Y minus 1, Z minus 1. This is the PQ from the formula, not the PQ in this equation or this problem. And then I need to dot it with the normal vector, 1, 0, 1. This should equal 0. So what I see is I get X plus Z minus 2 is 0, or X plus Z equals 2. And a good thing to do, a good habit to get into, of course, is to always try to just double check your work. And I highly recommend this on an exam, if you're doing a problem like this on an exam. As you saw when I was calculating PR here, I made some mistake. I was calculating QR instead. So it's easy to make little mistakes as you're doing this. And the thing to do at the end is just double check. Do these 3 points satisfy this equation? So 1 plus 1 does equal 2. 1 plus 1 still equals 2. And 2 plus 0 also equals 2. So all 3 points satisfy that equation. There's only going to be one equation up to kind of multiplying both sides by a number that works. So this works. As long as it's of this form, AX plus BY plus CZ equals D. Okay. Questions? Yes. This guy. Yeah, so this is, if I go back to the formulation of the equation, this is this vector here. So how did I get this vector? I said, give myself an arbitrary point, X, Y, Z on the plane, and look at some fixed point, P. Then this vector, the one you're asking about, is the displacement vector here. It's that displacement vector from P to that arbitrary point. So here I chose P here, but as I sort of warned, I don't want, that Q is static, so I have some arbitrary point. And that's this displacement vector from P to the arbitrary point. Okay. So let me just, I've got about 3 minutes, it seems. So let me give you guys one more. I'm not going to do this in full, but I would like to share this with you because this certainly will come up on homeworks and maybe on an exam. But read about this in the book, of course. So let's look at a problem, compute the distance between a plane, say X minus Y plus Z equals 1. There's an equation for a plane. And the point, say 2, 0, 1. Okay. So in order to compute such a quantity, what you're going to need, again, is you're going to need those two things that you're looking for the plane. So we have a point P. I mean, well, what are we looking for here? Let's just clarify that before I say. So let's say this point, I call this point R. So R is sitting up in space. And just like with a line, what we're looking for is the shortest distance from R to the plane. So we want to drop R so that we make a, to whatever point we have here, that's going to be perpendicular to the plane. But that has a familiar ring to it, right? Perpendicular to the plane. Because in fact, we know that this normal vector that we have for the plane, that should be a vector that is indeed perpendicular to the plane. So maybe shorter or maybe longer. Let's say it's longer. So this is going to be our n. So to solve this problem, what you need to do is you need to extract, just like with the problem with lines, you need to extract that normal vector from the equation. And how do you do that? You again find a normal vector by looking at the coefficients of x, y, and z. So a normal vector for this plane, and again, they're only unique up to scale. This is going to be, say, 1 minus 1. Pardon me. 1. And then if you want to find this distance, the length of this dotted line, well, what you can do is if you have a point on your plane, again, you can find this vector from that point to the point R, say PR, and then project PR to N and take that vector's norm, right? In other words, if we project this vector here, and we look at this vector, this length here is going to be the length here. That should be a rectangle, right? But that length is the length of that projected vector. So the formula, which you can read about in the book, is going to be the following, and I'll just write it down and we'll stop there. So the distance is going to equal the norm magnitude of the projected vector along n of PR. Now, how do you find P? There's one thing we didn't see. We saw how to find the normal vector from the equation, but how do you find P? Well, that's easy. You can just say set x equal to 0, y equal to 0, and z equal to 1. That will satisfy this equation. So just find a point on the plane and then calculate this quantity. Okay, thank you, everybody. See you on Thursday.